Howdy. Today I'd like to share with you a very useful technique for finding derivatives of complicated functions, especially functions that have variable exponents or functions that have complicated multiplication and division. Now tomorrow, after your quiz, we're going to explore this method a whole lot. I want to just introduce it to you so that you can be chewing on it in preparation for class tomorrow. And so we're going to focus on a function that has a variable exponent. We're going to take a look at y equals x to the x power. And what we would like to do is to find dy dx. And the problem that we have with this particular function is that it is not an exponential. Because the base, which is x, is not constant. My functions y equals 3 to dx or y equals 1/2 to dx are exponentials because they have constant bases. We know the derivative rules for these. Y prime is equal to 3 to dx times ln 3, and y prime is equal to 1/2 to dx times ln 1/2. This fellow right here has a variable base, and also I cannot use, it is not a candidate for power rule. If I have y equals x to the 5th, or y equals x to the 1/3, then I can use the power rule to differentiate, because I have a constant exponent here. Just like that. But this guy, he's not either one of those. We have a variable base, and we also have a variable exponent. And that in particular suggests that our technique might be useful. And this technique is called logarithmic differentiation. Logarithmic differentiation is kind of what it sounds like. We're going to use logarithms in order to transform the problem into an easier problem. Specifically, we're going to use log properties to convert problems with multiplication into addition problems, problems with division into subtraction problems, and problems with exponents into multiplication problems. Because of our three log properties, the log of a product equals the sum of logs. The log of a quotient is equal to the difference of logs. And the log of a power is equal to power times the log. So we're going to use these three log properties to turn complicated problems on this side into simpler problems on this side that involve addition, subtraction, or multiplication. Let me show you how that works with our particular function. The basic plan is I'm going to take the log of both sides of this equation, and then I'm going to use log properties to simplify, and then I'm going to use implicit differentiation. Watch how this works out. If we begin with y equals x to the x, and I'm trying to find dy dx, I'm first going to take the natural log of both sides of this equation. And on the right-hand side, I can now use my log property, the exponent property, to rewrite the log of x to the x as x times ln x. I have converted an exponent problem into a multiplication problem. Notice that we haven't done any derivatives yet. All we've done is algebra with logarithms. So if you're a step kind of a person, this is the first step. You take the log of both sides and do what comes naturally with log properties. Now, in our second step, we're actually going to differentiate. And this is familiar to you by now because you are well versed in implicit differentiation. On the left-hand side, the derivative with respect to x of the natural log of y is going to be 1 over y times dy dx. By the way, in logarithmic differentiation, this will always be the case because you will always end up with natural log of y on the left-hand side. On the right-hand side, we have product rule. And when we simplify here, the derivative with respect to x of natural log x is 1 over x, and the derivative of x is 1. And we just happen to have something nice occur here, that is x divided by x is 1. And of course, ln x times 1 is just ln x. On the left-hand side, nothing has changed. We still have 1 over y dy dx, and we are looking for dy dx. So we're going to multiply both sides by y. This is a perfectly good answer, but it is not explicit because we have an answer in terms of both x and y. And the original function was given to us explicitly. Y is a function of x, and therefore we would expect that the answer should be also. So to get it there, we're simply going to substitute. Since y is equal to x to the x, then y is equal to x to the x. And we can substitute, giving us dy dx equals this very interesting result, 1 plus ln x times x to the x. We're going to do some more of this tomorrow, but I wanted to give you a sneak preview.